we're going to be deriving the expression for a steady state absorption flux of a gas A in liquid with thickness of whatever you want, but we'll just say certain thickness. And beyond that thickness, the concentration is equal to 0. Now that's a lot of words, so let's visualize this. Drawing that out, we have our liquid, and our liquid is going to have a thickness. Over here is our vapor. And on the left side, after the film thickness of the liquid, we have our concentration of A equal to 0. Now, our reaction rate for this problem, reaction rate is K. And this problem is a first order, so we also know that this equation exists for our reaction rate. From here, let's label the film thickness as Z being equal to 0 on the right side and Z being equal to the total thickness on the left, because our vapor is going to be moving from the right to the left. And I want to start by doing our molar flux rate of A from Z equals 0 equals Fick's law. It's going to be negative diffusion coefficient of A, B, multiplied by the derivative of our concentration of A with respect to time. Now, why is the diffusion coefficient negative? Good question. Well, we are solving a problem where our flux of A, our molar flux of A, is traveling through a concentration that's going from a higher concentration to a lower concentration. So we're going to have a negative sign for our diffusion coefficient. Additionally, we can create another equation. We can say that the change in our concentration with respect to time is equal to negative, because we're moving from high to low concentration, change in our molar flux rate, right? Because it's going from the right to left, with respect to distance, because it's going from right to the left, or left to the right, plus our reaction rate, since there is a reaction going on. Now we know that our first order reaction rate is equivalent to this equation, so we can plug that into the one that we just derived. And we get this problem. So this is going to be since our reaction, our first order has a negative R, this is going to be negative since it's positive. Negative K reaction rate times our concentration of A. This is a steady state problem. So our left side of the equation will be equal to 0. There is no change in that. And we can substitute in our Fick's law for our molar flux of component A, or gas A. And what I'm also going to do is divide everything by the coefficient, a diffusion coefficient, AB. So that results in the equation 0 equals, it's funny, 0 equals negative, it's going to be positive, right? Second derivative of our concentration, second derivative with respect to the second derivative of our time, minus our reaction rate divided by our diffusion coefficient multiplied by our concentration of A. So we're looking for that concentration of A. I'm going to make this more simple to solve because we're going to be using differential equation concepts, and to do that I need to kind of get rid of this part of the problem, not get rid of it, but create a constant for it. So we'll have a constant M is equal to the square root of our reaction rate divided by our diffusion coefficient of A, B. So and then our second derivative is equal to, and actually make that positive, because we'll say we added we'll say we added this side over to here, but I'm just gonna write this on the left side anyways. is equal to our constant we just created multiplied by the concentration of A, but the constant is going to be squared since this is the square root and it's not in this equation we just derived. From here, we can use our differential equation or differential equation concepts that our concentration equals constant A sine hyperbolic sine of mz plus B constant multiplied by hyperbolic cosine of mc. And it's z because this is this is z. I did not switch that after I substituted in the Fick's equation, Fick's law. See, this should be z, and this should be z as well. We can look at the identities of hyperbolic sine and hyperbolic cosine. So for hyperbolic sine, that's equal to e to the x minus e to the negative x over 2, and hyperbolic cosine is essentially the same thing, just added together. Now, if we're solving for our problem, we're going to look at the boundary conditions, and if we want to solve for the concentration at the interface for these so we're trying to find the constants, right? And we're looking at our specific problem. So we want to look at the interface and the final thickness, and that's going to be the interface is z equals 0, and the final is z equals the thickness. And so these are boundary conditions. We'll just label that for information. So if we're talking about z, if z equals 0, we'll plug in the idea, these identities. We'll have a multiplied by e to the 0 minus e to the negative 0 over 2 plus b times e to the 0 plus e to the negative 0 over 2. Now, e to the 0 is 1, so 1 minus 1 is 0, so this whole entire problem part of the equation is 0. And then 1 plus 1 is 2. 2 divided by 2 is 1. So our concentration at our interface is equal to a constant B. Now for our thickness, it's going to be a little more difficult to solve this problem because we'll have that concentration A is equal to our constant A sine, hyperbolic sine, multiplied by m thickness plus B hyperbolic cosine times m thickness. So A is going to be equal to, since our B is also concentration, which should be concentration of hyperbolic cosine divided by hyperbolic sine. Yeah, this should also be negative concentration. And we'll say this is the concentration at the interface for all these problems, just so there's a differentiation. Oh, I wrote it there. So plugging this back into our original equation, we have our concentration is equal to A, which is negative concentration of A, the interface, hyperbolic cosine of m thickness, multiplied by our hyperbolic sine of mz, our distance c, all over our hyperbolic sine of m thickness. And this is added to B, which is concentration of B hyperbolic cosine of mz. So that's going to be concentration at the interface of cosine, hyperbolic cosine times mz. What you can do to make this equation come together is multiply this by sine of m thickness over sine of m thickness. Hyperbolic sine, of course. So that gets you negative concentration of A at the interface multiplied by cosine, hyperbolic cosine of m times the thickness multiplied by hyperbolic sine of m times the distance in c, plus our concentration at the interface multiplied by hyperbolic cosine to with respect to m times c times hyperbolic sine multiplied by m to the thickness, and this is all over hyperbolic sine of m to the thickness. Now there are identities that you can discover in order to simplify this down even further. Those are online. It's not usual, like what I'm trying to say is there are identities for certain cosines and sine combinations. And for this one, we can translate this equation we just derived into something that looks a little more like this. Our concentration at the interface times hyperbolic cosine of m z multiplied by hyperbolic sine of m thickness minus hyperbolic cosine of m thickness times sine of hyperbolic m z. And this is still all divided by hyperbolic sine of m thickness. And our final equation should look like this. Concentration is the concentration at the interface multiplied by sine of m times distance of z minus delta thickness over its hyperbolic sine of constant m times the thickness. Now we're going to do a blast from the past, and we're taking this concentration equation. We're going to go all the way back up to Fick's law, the original Fick's law right here, and we're going to plug it in. So we have our concentration, our derivative of our concentration with respect to distance. And so we really need to take the derivative of this equation. So taking the derivative of this equation with respect to dz, we get negative m constant of concentration AI at the interface multiplied by hyperbolic cosine of m constant thickness over hyperbolic sine of m constant thickness. And we plug this back into our Fick's law. Let's go up here and just write the final equation for our problem, which is Fick's molar flux of A, z equals 0, equals the diffusion coefficient of AB multiplied by negative m times the concentration at the interface times cosine hyperbolic of m thickness, or constant m thickness, divided by sine hyperbolic of m thickness. And that m is, of course, equal to the square root of our reaction rate divided by, where is it? Divided by our diffusion coefficient. And look at that. I mean, of course, you can cancel out the negative signs, so it's just the diffusion coefficient. And there's our final, oh, that's not a highlighter. There's our final equation for a steady state absorption flux of gas A in a liquid film thickness of whatever, while it goes to a place where the concentration of the gas is equal to 0. Steady state 0, we used Fick's law, we used reaction rate first order, we derived an equation using our differential equation identities, and then our sine and cosine identities, and plugged it all back into Fick's law to determine that this is our final equation for our absorption flux.